Hello everybody, and today I will be teaching a neural network called Generative Adversarial Network. So let me just write it. GAN for short. So this is the title for today, and this is a neural network that is behind deepfakes. So I'm sure, okay, let me explain what deepfakes is briefly. Deepfakes are, let me use a popular example, say videos, say images, say sounds of people doing, saying, or looking like what they've never looked like before, what they've never done before, or what they've never said before. So I'll tell you how it works in theory. So that gives you a better understanding of how it's created. So generative adversarial networks, the name generative, it generates things. And this is a type of deep learning model that consists of two neural networks. And they are called the generator and the discriminator. And I have said a popular example, deepfakes. And deepfakes aren't the only use case of adversarial neural networks, of generative adversarial neural networks. There are also positive use cases because, for example, it's used in the healthcare field for synthetic medical image generation. Also, even in movies, entertainment for the special effects. So it's not all bad. No. It's just that some people use it for bad, or could use it for bad, as AI keeps getting better and better. So now let me show you how this works. It's really interesting because these two, they go against each other. So it's like a gamification. So let's start. Let me use another color. So now this is how it starts. I said there's a discriminator and there's a generator. So the discriminator So it receives a sample. Shall I use the same color? It receives a sample. Let me just put this. I wanted to write it in caps, but then I changed my mind. So it receives a sample or an input. So this nature and it outputs a value. Let me write this bigger. It outputs just trying to see if the space is enough because we're gonna cover enough today, a lot today rather. So it outputs a value, and this value is its confidence level in predicting or classifying whatever sample it receives as either real or fake. So for example, if the value is 1, it means, write it on, it means it's real. But if its value, if it outputs 0, it means the sample, let me just say fake. Fake. So I hope you get this. And then if it's close to 1, it means it's to an extent really sure that it's the sample it received is real. And if it's close to 0, it means that it's almost certain that the sample it receives is fake. So sample means the data. I would expand more on this as we go, so I don't want to jump the gun here. Now let's talk about the second neural network, which is the generator. Let me just raise it up a bit. Like I said, we're going to cover quite a lot today, so I want it to be compact. I want everything to contain this. I don't want to clean anything eventually. So let me move this up. So the generator. This generator doesn't receive a data. This receives a data sample. The generator does not receive a data sample. Instead, it receives what we call noise. Random noise. And this noise basically means vectors or numbers. So now this noise is given or put into the generator. Space. And guess what the generator outputs? A sample. So you might already be seeing the correlation. If it outputs a sample, then this is a sample that goes into this. And so to explain, this sample can either be from the data, the real data set, because how it works is the discriminator. I'm jumping ahead of myself here, but let me just give a background. The discriminator is trained with the real data so that it learns what a real data looks like and how to catch the generator when it generates a fake data. So this sample could either be from the real, could either be a real sample, which is from the database, or could be a fake. Could be a fake, which is a forgery from the generator. So still stay with me. We going deep now. So now the question is, how is it that the generator is able to generate something similar to the data sets when it hasn't seen it before? So a very common or popular example to explain how generative adversarial networks work is the analogy of a counterfeiting operation. So in this counterfeiting operation, our generator generates the fake. Let me just put it there. Yes. Our generator generates fake bills, while the discriminator's role is to discover or determine which bills bill is fake versus real. So that is actually what they do. So in this example, we're using the analogy of a counterfeiting operation of forging fake bills. In another example, or when you want to train a generative adversarial network, you want to maybe, create a video of somebody doing what they've never done before. So the generator generates the fake video while the discriminator is there to catch the generator when it generates anything fake. So now both of them help each other to improve. As the discriminator gets better and good in catching any forgery by the generator improves to avoid being caught by the discriminator. So both of them are actually on their toe, like a cat and mouse, to ensure that this doesn't catch me, and this generator says, I want to ensure the discriminator doesn't catch me. The discriminator says, I want to ensure that I catch every forgery made by the generator. And together they help each other improve and be good. And eventually, when the GAN is trained, the discriminator is not needed anymore because the generator is good, and we just use the generator to generate new images. So now there's a table called the confusion matrix. That's actually a table that helps to evaluate how well the discriminator is doing to improve performances. And so we're going to use that confusion matrix to actually see the learning process between this generator and discriminator. So let's get into it. But quickly, before we draw the confusion matrix, I want to specify that the sample that the discriminator receives can either be a real, which is from the database, or from the generator, which is fake. So let me just write it here to specify. So it can either be real database or fake from the So let's go on to draw the confusion matrix. Confusion. You know why it's called a confusion matrix very soon. So let's start with, remember what a confusion matrix is. It helps evaluate the discriminator's performance to improve the performance. Yes. It helps evaluate how well the discriminator is doing in order to improve the performance. And this confusion matrix will guide us in the learning process, which I'm going to draw soon here. So just stay with me. Confusion matrix, actual, say true, right here, true or actual class. And let me write here, predicted class. So let me draw the boxes. So I'm gonna draw 4 boxes. Start from here. Start here. one more thing. Need to put this tag here, positive, means it's real, negative, which means it's fake, positive, real, fake. Okay, yeah. There we have a confusion matrix. See why it's called a confusion matrix. So this is called the true positive. This is the true negative. Now this is the false positive, yes. I'll explain all this soon. Give me time and comment. What? Let me just write it again. False positive. I'll explain soon. And this, you guessed right, false negative. You might already be seeing some synergies. Positive, negative. So let me explain. So this true positive is where the bill is real. And then the discriminator, let's say D for short, classifies it correctly as real or as positive. Now the true negative is where the bill is fake. And the discriminator classifies it correctly as fake. Now the only two tricky parts are this, and I'll give you a trick on how to actually get what false positive and false negative is, which is what I used. So now this bill, so think of it as falsely positive. So that means the discriminator falsely predicted it to be positive or real. So start with this, the discriminator falsely predicted it as positive or as real. So that will be real, but it was in fact fake. You see the trick? So if you can pause this video and try and get what this is using that trick. So falsely negative, it means the discriminator falsely predicted it to be negative or to be fake. So that means D for discriminator says it is fake, when in fact the bill was real. Do you get it? So I hope that has kind of clarified confusion matrix and it's not really confusing to you. Okay, so this confusion matrix I drew is just to help us understand the learning process itself. So let's get into the real deal. Yeah, so now the first step, first learning, what color do I use? Let's use lemon. So the first learning process now is, let's put it as A. it starts with, when I mean learning process, remember these two neural networks that the GAN consists of initially begins with random weights. If you watched my video on deep learning, you understand. So it just begins with random weights where the discriminator is just guessing. Could this be real? Could this be a fake? Could this be a real image? Could this be a fake foot? Could it be forgery? Could it be real? Randomly. So now it starts with the discriminator. So let me, this is where I kind of want to draw a line. Okay. So let's start. Moving this higher a bit. Okay, so A. So it starts with the database of real bills. So this database sends the real bills to, you guessed right, the discriminator. And then this discriminator can do either two. It could predict, let me just keep using this. It could predict, I'll explain soon. Predict as real or it could predict as fake. Stay with me. I'll explain all this soon. So now it goes to the loss function. Okay, amazing. Let me explain this first step. So now the first step is in the learning process or in the training process. You first of all feed or train the discriminator with the real database. So for example, we're using the bills here because this is our analogy. Let me just circle this so you know it's separate. because this is our analogy. So we put in or we feed the database of real bills to the discriminator. So it sends the real bills to the discriminator, and the discriminator initially randomly just classifies it anyway. It starts off, for example, just randomly classifying it real, fake, and here, if it correctly classifies it as real, good, because it's a real database. But if it classifies it as fake, then the loss function has a large value. So this first step focuses on the false negative. Why? Because if you remember, the bill is real, because we fed it with a real bill, but the discriminator classified it as fake. So because it classified it and it misclassified it as fake, the loss function would have a large value, and that would, in fact, this error would drive the discriminator to update the weights using backpropagation and optimization. So now that's the first step. So let's go to the next one. Now the second step is actually where the generator comes in. So random noise, call it, let's just say noise, or random noise. Remember what noise is? Vectors or numbers. I don't need to write it again. So this random noise is sent to, let me just make this shorter, because I'm going to be drawing two things here. So the random noise is given to the generator. And then the generator, of course, generates fake. So say fake bills, and sends it, and this is fed into, you guessed as much, the discriminator. Now the discriminator if a discriminator correctly so the two possibilities, if it says real, it could either say real or fake. It goes to the loss function. I hope you can see that now. So this is quite interesting. It's different. So this second learning step uses the true negative. It uses a true negative because, so starting, random noise, or which also means vectors or numbers, are fed into the generator, and this generator has the daunting task to come up and create fake bills from this random noise or numbers. And this fake bills is then fed into the discriminator, which now has to determine if it's real or fake. So now we're focusing on if it's fake here. The next step we'll talk about if it's real. So if it is fake, that's the true negative in the sense that the bill is fake and the discriminator actually catches. It catches. This is focusing on it's where the discriminator catches the generator's forgery. Forgery, yes, not surgery, yeah. Catches the generator's forgery. So now this loss or error function goes to the generator. Update. But something interesting, so because the discriminator correctly identifies the fake bills as fake, the loss function here is high. The value for the loss or the error function is high. Why? Because we want to train the generator to be able to be so good at forging fake bills or fake whatever as the case may be, so it bypasses the discriminator. And so this error drives the generator to update its weight through backpropagation and optimization. But because of the way backpropagation works, which starts from the discriminator's outputs and works its way step by step backwardly, it means that we have to go through the discriminator. We first have to calculate the discriminator's gradients to be able to get to the generator's gradient. So yes, we calculate the discriminator's gradient. We do, but we say here that it's frozen. Frozen means that even though the gradients are calculated, let me specify, even though the gradients of the weight of the discriminator are calculated, they are not updated. They're just calculated because we need to calculate them to be able to get to the generator and calculate the gradient for the weight of the generator. So we say here that it's frozen, it's not updated. So if I could just put it here and just say frozen. We calculate the gradient of the weight first of that of the discriminator, then calculate that of the generator. But because we're only focusing on updating the weight of the generator, we only update the generator. We don't update the weight of the discriminator. I hope you understand. So let's go to the third one, the third step rather. So the third step still follows the same, but it's just focusing on the discriminator this time around. So I'll just replicate it. So fake views. Trying to do some, yeah. You know what? Let me just write the view here. Okay, so, okay, I'm a bit sweaty. Yeah, so, the third step focuses on the false positive. False positive is where the discriminator falsely classifies a fake bill as a real bill. So, this loss function or error function connects to the discriminator. So the error drives the discriminator to update its weight so that next time it doesn't falsely classify a fake bill as a real bill. Now to the fourth step, which is the last learning step. The fourth step is basically a replication of the second step. For clarity's sake, let me just draw it again. So, okay, so then I'm literally just replicating it. Okay. Real, fake, yeah. So replicating it. I'm just replicating it for clarity purposes. So to update frozen. Okay, so let me explain why the fourth step is replicated. So remember, I said at the beginning that these two are like cat and mouse. They help each other to improve. They improve themselves and also in the process help each other to improve. So if you notice, the discriminator is getting feedback from the loss function in the first step, The second step, the generator is getting feedback. But the third step, the discriminator is getting feedback. So we have to double the only step where the generator is getting the feedback. We have to double it to ensure that both the discriminator and generator have equal opportunities to learn and improve. Get feedback from the loss or error function so that they can update their weights to effectively do their task. So since the discriminator learns from both the false negative and also the false positive, that's two rates, this generator only learns once from the true negative. So we have to double it so that they're both learning twice. And that way, we need to make them at even pace so that they're able to help each other improve and also learn at the same pace. So one more thing I want to talk about is that if you've noticed, there's no loss function that is directly connected to just the generator. This is because the loss function of the generator all by itself is irrelevant. And in most cases, we never actually need to define one, because since it's literally one big model, like you can see, the generator's output is connected to that of the discriminator. So the generator uses the loss function of both of the same model. It uses the loss function of the discriminator, which in a way is also connected to the output of the generator. So that's why we do not define a singular function, loss function for the generator. So, and that's it, because the goal is to have a discriminator that has a general and well and deep knowledge of the data set, of the real data it's trained on. And then on the other hand, we also want to have a generator that is able to create statistically indistinguishable fakes or forgeries that can fool the discriminator. So that's basically it, and I hope that I've been able to explain efficiently the theory behind how GANs are created, which is the deep learning model behind, technologies such as deepfakes and the likes. Let me know if you have any questions, and I'll be happy to answer them. Thank you. See you next week. Bye-bye.